Okay, good afternoon, everyone. So today we're very happy to have Saleem from the Mathematics and Computer Science Division at Argonne National Lab in the US, who is going to tell us about classical simulators as quantum error mitigators via circuit cutting. Zain, please.
So thanks for having me. This is the paper that is on our archive that I'll be talking about. Exactly the same name in collaboration with Ji Liu and Alvin Gonzalez. Yeah, and it's about using classical simulators as quantum error mitigators using the circuit cutting method. Okay, so motivation for this work. Quantum circuits are very noisy. In the current NISQ era, quantum error correction is not yet feasible. We don't have fault tolerant quantum error correction. In the absence of that, we can use various quantum error mitigation techniques like symmetry verification, polycheck check sandwiching. Many times these quantum error mitigation techniques require ancillary gates and resources, like you attach another quantum circuit with the main quantum circuit that you're error mitigating, and the risk that you run into is that like the error mitigation circuit that you have introduced will add additional noise in the circuit. So the circuit that you have like introduced is going to add more noise instead of error mitigate. So to deal with that situation, we introduced this this method called simulated quantum error mitigation. What it does is it separates the main quantum circuit and the circuit that you are error mitigating with into two partitions via the circuit cutting method. The error mitigation circuit is sent to the simulator. So the error mitigation is done errorlessly and without any noise, and the main circuit is run on the hardware. Now, what is circuit cutting? So this strategy is also called quantum divide and compute. So let's say you have a given arbitrary quantum state of n qubits. You can introduce this identity operator and resolve into a complete set of states like here, and basically divide the quantum circuit into two parts like here. Like this is a quantum circuit that you can run on one partition of a quantum hardware or on one quantum hardware, and this is another quantum circuit that you can run on another hardware. B is just a state that was introduced by like introducing the summation over like all the possible states in a Hilbert space, and psi Bn is a subnormalized state of n-1 qubits that we acquired by like projecting psi onto the state B of qubit n. Trouble with this is though that when this is run on another hardware and this is run on another hardware, there's still some phase information. There might be a phase difference, which like when you write a quantum state, when you resolve a state in this way, you lose the phase difference information between these two quantum circuits, which is very important for like recombination. So expressing a quantum state with a wave with a vector is not the best way to do it. This limitation that I described of like representing quantum state via a wave function can be overcome by representing quantum states with a density operator, whose diagonal entries, as we know in the measurement basis, define like a classical probability distribution over the measurement outcomes in that basis. So what we do is we decompose rho into conditional states. We can expand each m element of B. Here B is all the possible 4 directions of the block sphere, I, X, Y, Z, essentially. And when you represent it in terms of density matrices, so you don't lose any phase information, and this recombination essentially works. Here, lambda m denotes the spectrum of M. M here is the 4 directions, as I said, like the poly X operator, poly Y operator, poly Z operator, and the identity, of course, and MS is like the projections of the S projector onto the eigenstate MS of M. And via this method, you can essentially separate 2 quantum circuits. And the utility of this method is like, let's say you have a 40 qubit quantum circuit, but you have devices that are just 20 qubits. You can send one part of the circuit to one hardware, another part of the circuit to the other hardware, and then using this recombination formula, you can get the result for like the total original circuit. Now, essentially what you are doing is you are doing tomography here. And we know that tomography has exponential cost. So this is a costly affair, exponential in the number of cuts that you are going to require to separate a quantum circuit into basically 2 fragments. As I mentioned earlier, the tensor products that I showed here are a big bottleneck in the recombination. There are some simplifications that we can do to sort of combine the results faster. One simplification is that we can just post-process the conditional distributions. Each of these fragment probability distributions are related to each other via these formulas. Once we have like these 4 distributions, these 6 distributions, we can then combine the fragments according to this and the equation 3. In the circuit with k cuts, this post-processing reduces the number of tensor products that are computed from 16k to 4k, which is an exponential reduction in the number of floating point operations required to recombine fragment data. But as you can see, it's still exponential. So circuit cutting technique is like not a cheap computational technique. Another simplification we can do is, like, as I mentioned earlier, we had 6k probability distributions that we needed to combine. This characterization is overcomplete because 6k distributions are not all linearly independent. There's a relationship expressed by equation number 4 that you can use, and that's another simplification we can do, which reduces the number of fragments that to be characterized by 4kf. But and that makes sense because you need 4 the space operators on the Hilbert space of a qubit has like real dimension 4. But this bottleneck still remains, and this will be important, and I'll explain how we circumnavigate this issue. Another problem, I'm not going to cite or explain this work, but the reconstructed probability distribution will not generally satisfy conditions required of a probability distribution, such as like it won't be normalized, and there will be some entries that are negative. To fix that, we introduced a method called maximum likelihood fragment tomography. It's published in Nature Quantum Information now, and you can look up. Sorry about like the missing ref detail of like where of the journal, etc. But this is published work. But after using maximum likelihood tomography, basically you get a real probability distribution, and everything works. We ran some experiments on this. We took a clustered quantum circuit. Now, we designed it carefully such that like it wasn't too hard to fragment this this random unitary circuit that we have into parts by minimal cuts, just to study like what effect fragmentation has on the fidelity, or we'll be studying infidelity, but it's just the 1 minus fidelity is the infidelity. And the result that we saw is like for large number of qubits and more fragments, the result that you get from maximum likelihood fragment tomography has lower infidelity compared to if we run like the full circuit. This was done on a simulator, so the only noise that was being considered was shot noise, but it does show that if you have a large quantum circuit, it can be useful to fragment it and run it separately and then recombine, and the result that you'll get will have a lower infidelity than when you run the full circuit, which is kind of an interesting result. This is the one. This is part of the paper that I mentioned here. And as I told you, this is already published. Okay, so that was the circuit cutting. Now, let me introduce to you an error mitigation technique that we used. The SQUEM procedure that I mentioned works for other kinds of like error mitigation techniques as well. But in this one, in this paper, in this work, we use this technique called polycheck sandwiching, which is also published in scientific reports. It's in collaboration with Alvin Gonzalez, Ruslan Shadulin, and my ex-supervisor, Martin Sukara. So the way it works is this U is your original quantum circuit. You impose a constraint on this quantum circuit. See, these are poly strings, and you ensure via this quantum circuit that this condition is always obeyed. These are like control poly string operations. At the end, you post select on this on all the 0 states, and for all the for states with like all qubits in 0, you keep them and you post process the other ones out, which ensures that throughout the runs, this condition was always satisfied. And this is an error mitigation technique. Now, as I mentioned earlier, I would like to cut these extra gates and operators that I've introduced here to the simulator, because like having all these operations run on the quantum circuit or on the quantum hardware can introduce like noise of its own. These are like not easy operations to perform on a quantum hardware. But the trouble with this is that, as you can see, there could be many connections going between C and U and C and U here. And because circuit cutting is exponential in the number of exponentially costly in the number of cuts, this doesn't seem feasible to cut the error mitigation circuit out and send it to the simulator. The way we circumvent this is we will do qubit by qubit error mitigation. So in one run, we will only error mitigate 1 qubit, cut that qubit out. Like, so do you see where the red line is? This entire circuit goes to the simulator, and this entire circuit goes to the simulator. The main quantum circuit is run on the hardware. At the end, we get Pn probability distributions from each of these, from mitigating each of the n qubits. And then we use a Bayesian recombination formula of n output probabilities at the end and combine them to get the probability distribution of the original circuit.
Yeah, so Zain, I have a question.
Sure.
So when you say cut, you mean literally cut? Like what happens? I mean,
Cutting
once this is practical.
So tomography is happening essentially at the heart of it. What I'm doing when I'm cutting is I'm doing some let me go back. I'm doing some measurements here, and I'm doing some state preparations here. So basically, I'm transferring the information of this qubit, this output wire to this input wire via classical processing. So I've just basically understood what the state here is via performing tomography, by doing measurements in all 4 directions, and then I do preparations in all 4 directions. And that circuit fragmentation is row 1 is the density matrix for this fragment, row 2 is the density matrix for this fragment. I do all of this on either simulator or quantum hardware, depending on like what I'm doing. But then I'm recombining these probability these quantum states via this formula. That's what I mean by a cut. So it's just measurements on one side, learn what this output looks like, and feed it in here. And basically you can run these fragments now individually. I've like cut the entire thing out, and these are like now 2 fragments that I can run separately on quantum devices. I don't need to run them together.
I see. Yeah, thanks for explaining.
So if I were to cut these ones simultaneously, right? Like let's say I want to separate this entire circuit and this entire circuit out and send to a different device and run this on some other device. I'll need to do tomography simultaneously on I don't know how many wires there are, like, but it will be an exponentially costly operation. So I don't want to do that. I don't want to cut like the entire thing all at once. What I'm going to do is I'm going to error mitigate 1 qubit at a time and send, and then do exactly like the fragment recombination formula that I showed you. And that way I can do this without the exponential cost. So this can then be done in polynomial time if I do it one qubit at a time. Tomography is one of the most expensive computationally expensive operations in quantum computing. Okay, how does the Bayesian recombination formula then works? So you have each classical state in the computational basis. It is represented by a binary string given by this, and SK indicates the kth bit in the S string. I defined something called the bitwise probability distribution, which is very important. So for a distribution P, the probability of qubit K having a measured result 0 over all states is denoted as, is given by this formula. And similarly, the same formula applies for W1, where like this quantity basically tells you what is the probability, bitwise probability of a particular bit in a particular string being 0 or 1. This formula might look complicated. You haven't worked on this, but I'll tell in simple words. It is when I mitigate the kth qubit, this basically is the ideal bitwise probability for qubit K with outcome 0. And we want to move our noisy result. We had a noisy result. We error mitigated the kth qubit, and we want to move the kth qubit to the mitigated result. So for that, we use, we start with the unmitigated probability distribution for the string S. We update it via this formula, where Wj is the mitigated bitwise probability distribution over the unmitigated one. And as we keep updating these probability distributions via this formula bitwise, and apply the stopping condition that PR, the unmitigated one, gets as close to the mitigated probability distribution, we stop the algorithm. So what we are trying to do is, essentially, we go to a qubit, we mitigate it, we compare the result to the unmitigated one, and we update it such that each of the probability distribution goes as close to the bitwise, basically, probability distribution that was obtained from mitigating it. And at the end, we recombine the result, and we do this qubit by qubit. As you can see, this is for each of the strings, and the sum here is over all the bits. So when the unmitigated probability distribution gets close to the mitigated one, we stop. Okay, now we are going to apply basically this this error mitigation technique to an algorithm that's like really popular in the NISQ era called the variational quantum eigensolver algorithm. The objective here is to approximate the ground state of a many-body system. It doesn't require fault-tolerant quantum information, quantum error correction, because fault-tolerant quantum error correction requires like a lot of physical qubits, like coherently working together. But in this one, as you can like perform quantum error mitigation via a method that I just showed you earlier. These are all physical qubits that are acting as logical qubits as well. There is no encoding of logical qubits into of physical qubits into a logical qubit. The way variation quantum eigensolver works is consider a Hamiltonian with eigenvalues and eigenstates given by equation number 9. We know from the Rayleigh-Ritz variational principle that for an arbitrary quantum state parameterized by parameter theta, there is always a lower bound given by equation number 10. So we can optimize theta, like keep on doing gradient descent or any such algorithm on equation 10 to find a closed upper bound to E0. So the variational quantum eigensolver algorithm can be mathematically described as basically equation number 11. You're performing a minimization on theta of this expectation value, where U theta dagger acting on the 0 state is basically an arbitrary variational quantum state, which can be prepared on using a quantum circuit, and H is the Hamiltonian. Perform the minimization over theta till you can approximate this lower bound. The expectation, this is a hybrid variational algorithm, because these expectation values are measured on a quantum computer, whereas the minimization is done on a classical computer. So I borrowed this picture from a review on variational quantum eigensolver that got published by Tilly et al. In 2022. I do recommend to check it out. It's 150 pages long. It's pretty heavy, but yeah, variational quantum eigensolver is an important algorithm in the NISQ era, so I highly recommend people reading it. In summary, what's happening in the variational quantum eigensolver is you have a fermionic second quantized Hamiltonian here. You can convert it into a sum of polystrings, weighted polystrings, polyoperators via an encoding such as Bravik-Kitaev or Jordan-Wigner transformation. You can group the commuting terms together, perform calculate the expectation value of the Hamiltonian in an arbitrary quantum state, do gradient descent on the parameters, and update the parameters. This update, this variational quantum state can essentially be created by a variational quantum circuit, where like each of the gates is parameterized by some variational parameter like theta, theta 1, theta 2, theta 3. And basically, this is the part that you can do on a quantum computer. People have been doing this classically via this method, but the quantum aspect here is that this variational state that you have here can be prepared as a quantum circuit. And then you perform measurements and basically do this recombination of these measurements of these sum of polystrings and get basically and drive the Hamiltonian, the expectation value of the Hamiltonian to basically the lower bound provided here, and find the lowest eigenstate of the system. So we ran the VQE circuit with a hardware efficient ansatz. You can have different ansatz here. The one that we used is an ansatz that looks like this, where you have like single qubit gate operations, and then 2-qubit, and in between combining these single qubit gate operations are these C0 gates that entangle the different qubits together. We tested our SQUEM procedure of like error mitigating 1 qubit at a time and combining all the probability distributions to get the final probability distribution for lithium hydride, beryllium hydride, hydrogen fluoride using 4, 6, and 8 qubits. For BEH, using our protocol, we came pretty close. Like this is 0.001 difference between the noiseless simulation result and us running on the hardware. Oh, and one more thing. So each of these updates, like every time you run this whole one iteration of this algorithm, you have to update the thetas, right? Like, but the quantum circuit with updated thetas is a different quantum circuit. We didn't error mitigate each of those quantum circuits because that would take too long. We ran this on the hardware. We fixed the parameters at the end, such that like that fixed parameter quantum circuit is the one that we can quantum error mitigate then. And that's what we did, and we achieved results that are very close. Just to show you the final pictures of like what we saw. This is the energy that you get if you just don't error mitigate the quantum circuit, and this is the noiseless ansatz result. This is pretty far from the noiseless ansatz result. Okay, now we also did the experiment where we didn't send the error mitigation circuit to the simulator. We error mitigated everything on the quantum hardware. This is the energy you get if you just error mitigate qubit 0, error mitigate qubit 1, error mitigate qubit 2, and qubit 3. These are very far from like the energies that you should expect when you recombine these probability distributions via the probability via the Bayesian recombination formula that I mentioned earlier. You get a result that's still far. Whereas with SQUEM, when we send the error mitigation circuit to the quantum simulator, you can see that we are progressively inching closer to the noiseless ansatz result, which is the best you can do with the ansatz that we were using. And when we recombine, we sort of match very closely the noiseless ansatz result. We did this for like a larger molecule, hydrogen fluoride. It has 8 qubits. And again, actually, we were even surprised by this result, how just sending the error mitigation circuit to the simulator sort of really improves your result. Yeah, that's.
Great. Thank you very much, Zain, for the first part of the talk. So before moving on, you wanted to give a second part, right, Zain?
Yeah, I have a second presentation that's on a different topic.
Okay, yeah, sure, that's fine. But let's see if there are questions on this part here. Any questions? Actually, I do have a question about these material when you're talking about hardware. What's the significance of these compounds that you have, lithium hydride and so on?
Oh, so this is the quantum computation is like at its infancy. So this is well, quantum chemists would laugh at us essentially. They can do these calculations really fast, but we are incrementally trying to like go to higher and higher molecules, but these are like the smallest ones that you can actually run on a quantum hardware. and get a decent result. But I was presenting this to a quantum chemist, and he said, well, for these molecules, we can achieve 10 to minus 6 accuracy. Well, we were like a 10 to minus 2 or 10 to minus 3. But this is a state of like what kind of quantum computers we have. This has nothing to do with the algorithm, because like very few algorithms can do like, I don't know if there's an algorithm that can do like a better job than the one that we found here on the quantum computer.
But these materials seem to be correlated with number of qubits. So is there a
yes, the smallest ones. We have hydrogen fluoride is like the 8 qubit one. And then we started with the lithium hydride, which is like 3 qubits. So slowly, we are like moving up. The IBM competition announced right now has requires like to win that IBM competition, you have to find the ground state of a 12 qubit system.
I see.
Like, probably classical, very easy to do. But the method can be generalized in the future to 100 qubits and 200 qubits. That's the hope.
Sure. Yeah. It seems promising. Yeah. Sounds good. Any other questions on this part?
Yes.
Yeah, go ahead.
Yeah, this is Amaria. Hi, Zen. Nice to hear you.
Hi. Nice to meet you.
Okay, I was wondering about the answers, the importance of answers. You said hardware efficient answers. The answers is same for whatever kind of molecule you are using?
So there are different ansatz, and they all come with different costs, right? Like this is the simple one where the 2 qubit operations don't have a variational parameter on them. But you can use another ansatz, which is called the unitary coupled cluster ansatz, which tends to have variational parameters on the 2 qubit rotations as well. Recently, I've discovered that there are so many ansatz that it's like a lot of the times it's hit and trial. Basically, there's a cost you have to give for them. And also like we used a single layer, so you can basically have multiple layers of this. That's another thing you can do with the ansatz. But the ansatz is basically your choice, and its choice is driven by like the symmetries of the problem or hardware efficient. This ansatz is called the hardware efficient ansatz because it's like easy to map to a particular hardware. But then there's other ansatz that's like does a better job with the entanglement. Currently in quantum computing, like it's always a cost benefit analysis that you're doing when you're creating an algorithm.
Yeah, okay. Thank you.
Any other questions on this part? Okay, great. If not, let's move on, Zain, to the next part.
Second talk should be just, I think, I'll try to give it in 10 minutes.
It's okay, you have time.
And might be of more interest to the, I'm assuming I'm giving a talk in the physics department.
Sorry?
I'm giving the talk in the physics department right now, right?
This is really combined. It's a Center for Quantum Topological Systems. So we got math, physics, and chemistry, actually.
Okay.
Yes.
All right. Anyway, this is more physicsy. The other one was like very algorithmic and computer sciencey.
Yeah. Good.
Okay. So our target here is to figure out what's the optimal time for measurement in an open quantum system. By open quantum system, I mean a quantum system that has decays in it. This is also on arXiv and was done with Anil Shaji and Stephen Gray. Stephen Gray also works at ANL, and Anil Shaji works at an institute in India. Okay, so the tool we'll be using to figure out like what the optimal time for measurement in an open quantum system is the quantum Fisher information. it concerns with estimating unknown parameters of a quantum system. For simplicity, we'll focus on the case where like the Hamiltonian is being parameterized. Well, Hamiltonian can have various different parameters, but we are going to estimate only single parameter. Now, why is the quantum Fisher information important? It's important because of the quantum Kramer-Rao bound. Quantum Kramer-Rao bound is given by equation 1. So if you measure theta, the error in the estimate of theta is lower bounded by the inverse of the quantum Fisher information. So the larger the quantum Fisher information, the smaller the error in the estimate of theta, and the more accurate your measurement is. Okay. So just to explain what QFI is, quantum Fisher information is the quantum generalization of the classical Fisher information, which is the quantity that's used to find out the statistical distance between two infinitesimally close probability distributions. So the DS, the statistical distance between two probability distributions, can be expressed as equation 2, where Gij is symmetric defined on the statistical space, and classical Fisher information is related to the derivative of this statistical distance squared, essentially. The same thing happens in quantum mechanics. You can instead of dealing with classical probability distributions, you can quantify the statistical distance, or maybe quantum distance. I don't know what to call this distance. It's usually called Burris distance because of Burris introduced it. But you can define a distance between two infinitesimally close probability density matrices. So the probability distributions in quantum mechanics language get replaced by density matrices, and then you can define a distance metric on this, where L rho sort of acts like it's a super operator that acts like the metric, and D rho is like are the density matrices, and exactly the same sort of formula. Quantum Fisher information is related to like the derivative of the Burris distance between the derivative of the Burris distance with respect to theta squared. And there's a bunch of other things that I'm going to skim over, but like L theta here is called the symmetric logarithmic derivative, and there are some reasons related to commutativity why this is introducing this is a good thing to do. So we'll study like the quantum Fisher information, the time dependence of the quantum Fisher information. So as I showed you earlier in equation number 1, the larger the quantum Fisher information, the smaller the variance in the estimate of the parameter. When you plot the quantum Fisher information for an open quantum system with respect to time, you see that the QFI has a peak in terms of its magnitude and time. And that peak suggests that there might be an optimal time to perform the quantum measurement in this open quantum system. The formula we used in practice for calculating the time-dependent QFI is given by equation number 6. As you can see, the numerator is directly proportional to how fast your density matrix is changing with respect to the parameter theta. Lambda A and lambda B are the eigenvalues of the density matrix. So the larger this quantity, the smaller the error in the estimate, and that's the point that you should basically perform the quantum measurement. That's our conjecture when we start. So let's start with an n qubit. When a system where n qubits are coupled to a resonator, the Hamiltonian is given by equation number 7. The evolution of this density matrix is governed by what we call the Lindblad equation. My collaborator worked with like one of these guys, S. Sudarshan. So he insisted that we call it GKSL evolution, but in literature, most of the people call it Lindblad evolution. To make the problem analytically tractable, in the beginning, we'll restrict ourselves to the single excitation manifold. By that I mean there's only one excitation only one excitation states, like states that look like this. And this limits the dimensions of Hamiltonian to n plus 2 or times n plus 2 instead of like 2n times 2n, which becomes very hard to deal with. Now we have also realized that like for Hamiltonians that are like symmetric like this, that have permutation symmetry in the order of qubits, you can basically go to large excitation manifolds and basically not have to pay that computational cost. But that's something we are working on right now. So the relevant states in the Hilbert space are 1, 0, 0, 1, 0, 0. We are just going to restrict ourselves to n is equal to 1 case. We are going to apply the decay only on the resonator state, in which the resonator is excited. We use the decay value to be 0.15 electron volts. The coupling between E and F state is given by G, as you can see here. The resonator and the qubits are coupled via this. And we are going to basically measure the coupling between the resonator and the qubits. Now, let's study the state occupation dynamics. The F state decays, everything is going to the sync state, and the resonator state, excited resonator state gets up, but then it goes down because of the decay that we have applied there. Okay, now interestingly, when we plot the quantum Fisher information that I showed you earlier, it seems to peak when the dynamics of like the system have basically passed down. Like the dynamics are dead here at this point. The system is most dynamical around this region. So when we plotted this, we found this like very curious about like why this is happening. And just to remind you, the Fisher information was directly proportional to the rate of change of probabilities with respect to G. So we decided to introduce a new basically quantity, which we call the subspace adaptive quantum Fisher information, because we want to align the peak of the quantum Fisher information to the point where the system is most dynamic. So we are going to adapt the definition of QFI to the subspace where the state populations are mostly in the excited E and F state. Now, this is the relevant subspace, since as you can see in the Hamiltonian, the parameter is most sensitive to the dynamics that happen in this space, the E and F space. Another way of saying this is there's nothing that happens in the E and F state that cannot be explained by the PS state, because like all these probabilities sum to 1, or there's nothing that happened in the sync state that cannot be explained by just restricting ourselves to the E and F subspace. Now, we define this quantity SAF, we call it subspace adaptive QFI, and we plot this. Now, as you can see, the subspace adaptive QFI is perfectly aligning with the point in time where the system is the most dynamic. We calculated the rate of change of probabilities with respect to the parameter, and again, the subspace adaptive QFI closely follows the regions where like the rate of change is the maximum of the probabilities, whereas the Fisher information seems to peak when the system's dynamics are basically losing. We did this for like other kinds of collapse operators. We did it for the dephasing operator, and in this case, because the system is only going from F to E state or E to F state, the QFI and subspace adaptive QFI sort of align with each other and also maximize the point where the change is maximum. We did the same thing for detuning parameter, and again, the regular definition of quantum Fisher information has a peak that's way further in time when sort of the system dynamics have sort of passed. So our claim is that to find the optimal time to perform a quantum measurement is basically the peak where the subspace adaptive QFI is, and not where the peak of the quantum Fisher information lies. I'll skip this. So if you perform measurements classically, the best you can do is 1/n in like the scaling. The quantum Fisher information should scale as 1/n, or the variation of the parameter should go as 1/n. Whereas using entanglement entanglement, you can basically achieve this limit called the Heisenberg limit, where the where the scaling goes as 1/n squared, and that scaling is given by n. So we started with a G at G state, which is a very, very highly entangled state, tensored with the resonator state. And we actually saw that like you can actually break the standard quantum limit and improve your scaling to very close to the Heisenberg limit. We haven't done the large N case yet, but that's something we are working on. We did the same for the Dickey state, which is just a single excitation state, a sum of all the permutationally symmetric single excitation states. And again, we can do, since this is like less entangled, our scaling is slightly improved, slightly above 1, but not so much. In future, what we would like to do is we would like to calculate the quantum Kramer-Rao bound from fundamental principles where the subspace adaptive QFI is used. An experimental demonstration of the optimal time for measurement, collaborating with some experimentalists on this will be nice. Study the subspace adaptive QFI for the N excitation manifold, and basically investigate how we can use entanglement and the optimal time for measurement to break the standard quantum limit. Yeah. I can't actually hear you.
Oh, I'm sorry. I was muted. I was saying thank you so much, Zain, for both talks. And I'm asking if there are any questions. Sorry, I was muted. Any questions for Zain? So what's the relation between entanglement and I mean, how does entanglement show up here in this approach?
So entanglement is a quantum resource that you can essentially, it's the starting state that you start with. So that's something, what you have in your hand is what kind of state you want to prepare. If you are preparing a state that's not entangled, then you are basically not taking any advantage of the quantum resources that you have. And you can show that using entanglement or like quantum mechanics, you can improve the scaling. So delta theta is supposed to, if you have n systems and you just like perform measurements of some parameter on those n systems, the variation in the parameter goes as 1/n. But in quantum mechanics, you can show that 1/n is like the number of systems that you have. So, but if you entangle all of these systems together and the system is closed, you can show that delta theta goes as 1/n squared. So entanglement basically helps you reduce the variance in the measurement of your parameter. And what we are trying to do here is we are going to prepare a highly entangled state and then perform quantum measurements on it and see if we can break the scaling. That's achievable just by like by classical measurement.
I see. Okay. Thanks for explaining that. Sounds interesting. Any other questions? Any further questions on the second part? Okay, if not, let's thank Zain again for the nice both talks. Thank you. Okay.